Okay, so good afternoon, everyone. Welcome to this course, which is titled FPGA-based Accelerator Design. So this, along with me, Dr. Padmini from Xilinx will be co-teaching this course. Now, Padmini, would you like to introduce yourselves a bit?
Sure. Thanks, Suresh. So, hi everyone. So, I work at Xilinx in the software and AI products group. So, looking forward to working and learning from all of you, and also, sharing what I know with all of you. So, FPGAs are being increasingly used for accelerators and offloading all types of computation. So this is both a very relevant and a very current topic. So looking forward to.
Okay, great. Thank you, Padmini. So along with Dr. Padmini, we have Dr. Lavanya, who will also be helping us in this course on and off in guiding projects and here and there. So I think she is not here yet. I'm not sure if she joined us today. I'm not able to see Lavanya. Okay, no problem. So I will introduce you to Dr. Lavanya maybe in the next class. So this course is going to be exciting. I am particularly excited because there are many ideas to learn. Although in the computer systems group, we have been working with FPGAs, but I didn't get a chance to actually dabble with them and try out things by myself. I would like to take this course as an opportunity to learn, to experiment, to do new things, to learn new things along with all of you. So today I'm using a new setup for this class. Because of that I'm moving around and fiddling with things. Apologies for it. So at the end of the class, I will tell you a few important points. The first thing is, like all of you could be wondering, so if you have to work with, this is a course which is where we use FPGAs, where we learn how to design things targeting FPGAs. But this is an online course. How are we going to get access to FPGAs and actually try them out? So fortunately for us, so with Dr. Padmini's help, we are able to get access to AWS Educate Cloud resources. So we will be running our, you will be doing your assignments and projects on AWS Cloud. Yesterday, in the last couple of days, have been working with a colleague of Dr. Padmini, and it's a lot of fun trying to figure out things on how things work on AWS Cloud and work with the cloud. Because one interesting thing, really, yesterday I felt high is so as you will see later on. So we will do in the initial design phase, we will be testing our design using, you will be compiling and testing our design probably in an emulation mode. And then later on, we will actually deploy it on an FPGA. And so it turns out that the FPGA instances on Amazon, they are very expensive. So we have to be careful. So we have to first do all our pre-work using a low-cost instance, and then go to the actual F1 instance where we can run our design. It's a very nice experience yesterday for me, because so we did all these things. We built a kind of a virtual machine. We ran the initial, do the basic stuff, the pre-testing stuff, pre-hardware testing stuff on a virtual machine. And after it is all done, all in order, I was wondering, how I will take this design and run it on an F1 instance. It's all lots of things were running in my mind. And all we have to do is on Amazon Cloud, you just change the instance type on which you run your virtual machine image. So that's all extremely simple. So that means you all you kind of work on one system, you do everything, and after everything thorough testing is done, you just have to change the instance type, and then that's it. You will get access to an F1 instance, and your whole environment will be now running on that F1 instance. I found it to be extremely cool. So anyway, so that's we will talk about those things in the next week session. But the important point is you will be using AWS Cloud in order to do assignments in this course, in order to do projects in this course. And it's going to be a very fun learning experience. So today I would like to give some background on some background on architecture, some background on very little introduction to FPGAs. In the Saturday session, Dr. Padmini will be taking the lecture, the Saturday class, and she will give you a more detailed introduction to FPGAs. Today, we will kind of look at a bit of architecture and accelerators, things like that. So this is an overview lecture. In the next lecture, we will take a deeper look and we'll proceed further next week. Okay. So all of us are aware of von Neumann model of computing. That's what you as students you will be introduced to when you join your undergraduate program. Like for example, you have learned you do C programming course where when you write a C program, there is a single thread of computation in your C program. There is a single thread of computation in your C program. And then in the computer systems organization course also, you will learn instruction set architectures, and you will learn about processors, the design of processors, at least to some level. Again, there also, you can see that it's a single thread of execution. And this is what is called as a von Neumann model of computing. And that's what you will be exposed to, you will be introduced to when you join this program. Okay. So now if you take a step back and try to look at the computing landscape, you will see that computing is deeply embedded everywhere. So usually when we talk of computers, the desktop machines or the laptops that we use, they constitute probably less than 5% of the overall computing systems. And like the mobile phone, which is there in our pocket, it has a very powerful computer. Okay? It's extremely powerful. It can do lots of things. And then, so on one side you have here, let me see. So if you see here, this is where the computing is there in the miniature form. And if you come across this diagonal, you can see the data centers. In data centers, again, there are tons of processors, computing systems are present. So on one side of the spectrum, we have the deeply embedded computing systems in your smartwatches, Google goggles, or in self-driving cars, or even in regular cars also, there will be lots of microcontrollers which does a variety of things like speed control, cruise control, brake control, things like that. And then, of course, now the latest buzz is Alexa and all this stuff. So the deeply embedded computing systems, they are not quite visible to us, okay? But they play a very important role in variety of tasks that we do in day-to-day life. Similarly, the data centers, we will be using Google all the time to search for things, but we never, whenever you give a search query, it goes to a massive Google data center, and the results for that query will be processed. The query will be processed in the data center, and the results will be transferred back to you. And of course, Internet of Things, that's the latest, again, the latest buzz. So anyway, the point here is computing is deeply embedded in our daily life. And 95% of the computing systems, we don't even perceive them. Okay, they are just, they do their stuff behind the screen. And only maybe 5% of the computing systems we directly interact. That is usually our laptops, desktops, and mobile phones. And again, this picture you see here, it is an interesting picture. So the computing systems, they can be kind of, we can have an organization of computing systems. Like we have all these edge devices, your smartwatches, or temperature sensors, and all these things which are there at the end. So these are the edge devices. And these edge devices, they are present in billions. Okay, because they outnumber probably the number of human beings. Okay, so there are these edge devices are present in billions, and these edge devices, multiple edge devices, they can communicate with one or more fog nodes. And one or more fog nodes, they could be communicating with a data center. Like for example, in your home, in smart homes, there could be many edge devices, and those edge devices could be talking with a Google Assistant or with an Alexa system. You can think of Alexa as a fog node, and multiple such Alexas across your colony or across the world, they could be talking to the cloud. So when there is a computational task, whether you want to perform the computational task at the edge or at the fog or at the cloud, it's an important design decision that we have to make. So it depends upon the application needs, it depends, and then that in turn decides how we would like the architecture of the system to be like, etc. So I would like you to remember this important thing, this edge, fog, and cloud setting, which is a very popular thing which is a popular framework or an architectural framework which people use. But what is interesting here is whether it's an edge device or a fog device or a compute system on the cloud, the underlying architecture of the system is the same. So every computing system, it will have a processor, it will have main memory, it will have a bunch of IO devices that constitutes the hardware of the system. So that constitutes the hardware. And then on the top of this hardware, we have operating system or system software. And then on the top of the operating system, we have the application programs. So independent of what kind of device that we are talking about, the underlying computing system architecture, it looks like this. We have a hardware, we have a system software layer, and then we can have a application program, and then application program sitting on the top of system software. Of course, depending upon the device, how thick the system software is, for example, could vary. Like if you take Raspberry Pi, it may have a proper Linux operating system sitting on it. But if you take a microcontroller, you may not have a Linux operating system sitting on it, but some basic monitor operating system. We don't even call it operating system. Some kind of basic routines could be present on a microcontroller, right? So, and then similarly on a server, a processor, you may have a very powerful Xeon processor, but on an embedded system, the processor power could be less because it is optimized for power consumption. We want to use less power on an embedded system while trading off with the compute performance. But on a server, no, you may not worry so much about the power, but you actually care about the compute performance. How the system is optimized depends upon whether we are at the embedded systems end or at the server end, or we could be falling somewhere in between. But the basics system, it will just be this. Okay, so hardware and software. And here, the success of this approach, if you see here, so this you could have studied in CSO, but still I would like to recap this because we would like to make a point here in this course. That is, if you look at this thing, we have the hardware, and on the top we have system software and application software. So what makes the whole thing the whole engineering task feasible or amenable is the hardware designers, the processor designers, they expose this instruction set architecture to system software and application software developers. So the hardware designers, they provide this abstraction layer. They provide this abstraction layer. Instruction set architecture, it's an abstraction layer provided by so instruction set architecture, it's an abstraction layer provided by the processor manufacturers. And software developers, they use this abstraction layer and they build the rest of the system, the software stack, be it system software or application software stack. And this instruction set architecture, so it's very interesting. Once we have this instruction set architecture, the same instruction set, for the same instruction set architecture, IS64 instruction set architecture, there can be multiple hardware processors that can be manufactured. right? So AMD can have its own set of processors for the same x86 64 instruction set architecture. Similarly, Intel can have its own set of processors for the same x86 64 instruction set architecture. But as long as the semantics of the instruction set architecture remains the same, so the system software or software developers, they don't need to worry about whether the underlying processor is an x86 64 processor, whether it's a processor from AMD or it's a processor from Intel, it doesn't matter. Well, that statement is not completely true. The reason being, while the semantics of the instruction set architecture are perfectly remain the same, but the performance to some extent depends on how the instructions are realized in the hardware. So depending upon that, the compiler and possibly parts of the operating system may need to be redesigned, especially the compiler. If the compiler knows, this compiler, the instruction set architecture is still the same, but if you are targeting a Intel processor, maybe it has to generate code in a certain specific manner so that the program performance will be good. Similarly, if a compiler is targeting same instruction set architecture but an AMD processor, maybe it has to generate instructions in a different way so that the program performance will be good. All right. But the important thing is this, the most important thing is the abstraction. Instruction set architecture, this line, is an abstraction for the software to interface with the hardware. And because of that abstraction, the processor manufacturers, different processor manufacturers or the same processor manufacturer can keep coming up with better and better versions of the processor for the same ISA. Just give me a minute. Yeah. Great. So if you have any questions, please unmute yourself and ask. So, or put it in the chat box. We can keep this class interactive. It's a small class. So if it is interactive, it will be more fun. And then if you look at this one, if you take a little bit deep dive into the instruction set architecture, it kind of tells the statics of the system. Like, for example, it says what is an add instruction. So if there is an instruction like add R1, R2, R3, then that means the semantics of this instruction is you add the contents of register R2 and R3 and store it in R1. Okay, so the instruction set architecture defines what are all the instructions that are present in the ISA and the semantics of those instructions. And when we go to the dynamics of the system, is once you give a program for execution, there should be a model for execution for the dynamics of the system, how the program state evolves. So as you know, so in the von Neumann model of computing, we have this memory. This is your this is your memory and this is your CPU. You have your CPU. This is your RAM. And your instructions are present in this, your instructions are present in the memory. So you have an add instruction, you have a subtract instruction, so on and so forth. And the von Neumann model of computation says that the CPU fetches an instruction. So, and then there's a special purpose register inside the CPU, which we call as a program counter. The program counter contains the address of the instruction that needs to be executed. So whatever the address that is present in the program counter, the CPU goes, fetches the instruction that is present at that address. It decodes that instruction and it executes the instruction and it increments the program counter. So it usually increments the program counter, but at some point, if it hits a branch instruction, the branch instruction could be an unconditional branch or conditional branch. So depending upon the outcome of the condition and depending upon the branch target address, instead of fetching the next instruction, the processor will fetch the instruction that is present at the branch target address. And of course, the program counter register will also be modified accordingly. So here we have the processor and there's a program. The instructions of the program are present in the memory and the instructions of the program are executed in a fetch, decode, execute fashion. So this is the von Neumann model of computing, sequential model of computing. So, but we don't write programs in assembly language except in your CSO course probably. We write programs in C programming language, C++ programming language, or some high-level programming language. And then we rely on tools such as compilers to map these high-level programs written in high-level languages into equivalent assembly code and finally into machine code. So these abstractions are lowered into a form which the underlying hardware can understand. So we rely on these tools to map the high-level language abstractions. We use the programming language abstractions to express the computational logic or the algorithmic logic, and they get mapped to the instructions coming from the instruction set architecture. And then from there onwards, the hardware goes ahead and interprets these instructions at the hardware level. That's what happens. Right. So here, the 2 points I would like you to remember, it is the abstraction that is the instruction set architecture abstraction. It is supported or it is realized at the hardware level, okay? Because there is a physical hardware which interprets the instruction encoding. And the abstractions provided by the programming language, okay, they are supported by the compiler. So whenever there is an abstraction, someone or other has to implement that abstraction for us. So now if you compare let's look at the abstractions provided. So these high-level programming languages, they provide nice abstractions, while loops, for loops, and if statements, etc. So because of all those reasons, it is easy to program. This is very, very important thing. So it is these two, easy to program, hard to program. So if it is easy to program, then the productivity will be higher. Like if you have to build software using in assembly language, it will take possibly 3 months. Like for example, in CSO course, just to write an assembly code to find the maximum element in an array, how much effort you have to put in. But if you do the same in C programming language, it is much easy. And if you do it in Python, it is much easy. It's just one line. You just say list.max or something like that, and you have the biggest element in the list. So productivity. So that's the reason why people are behind Python, because we can write very complex, develop complex systems within a very short period of time using Python programming language. And assembly is on the other end, and C programming language is somewhere in the middle. And of course, if you write code in assembly, it is hard to read because you go and what is present in register R1 only the programmer knows, unless the programmer documents it saying in register R1 I am holding a loop index variable or something like that. So readability is a problem, and again it's hard to debug programs in assembly code as against when compared to high-level programming languages. In assembly code, it's not portable to new platforms because a program that is written for x86 64 instruction set architecture, you cannot run it on an ARM processor. And so code written in assembly, it is better performing when compared to code written in high-level programming languages. So this is kind of questionable, because what happens is when we write code in assembly, so you will have a lot of fine-grained control on the program. Because of that, you might be able to optimize a lot. But then, but when we write your program in C and you rely on the compiler, you rely on the smartness of the compiler so that it generates good code. But there is a, so this statement is true as long only under certain circumstances. So what happens is, if the application that you are developing is complex, then it will be hard for you to kind of wrap your mind around the complexity of the code that you are writing, and you will end up writing suboptimal code. So even if you are writing in assembly code, okay. So for large systems, so this is this assembly having a better performance than compiler generated code. It's not completely true. It depends on many factors. So the factors such as, number one, the size of the code, complexity of the code, size and complexity of code. Size and complexity of the code. So this is very relevant even when we talk about, think about FPGAs, because the equivalent comparison for when we, in the context of hardware design, is writing in assembly code. It is equivalent to something like you express your design in Verilog or VHDL. And then high-level programming languages, there are many approaches here, like HLS, OpenCL, Chisel, BSV, Blue Spec System, Verilog. So there are many high-level specification languages. So what happens is the same things that the things that we are talking about in this context, they are equally applicable there. Because, like, for example, only if the hardware design is small, then probably maybe your design expressed in Verilog or VHDL could be better. But as the complexity of the system increases, you may not be able to write such optimized Verilog or VHDL code. Number two is, again, in the context of compilers, if you really want to get good performance out of the system, you have to go beyond the instruction set architecture semantics and look for some other properties which will give you performance. Like, for example, if you have in the assembly code, if you write something like this, add R1, R2, R3, and subtract R4, R5, R1. So here, if you see, if you write a code like this, you can see there is what is called as a flow dependency between this add instruction and subtract instruction, because the destination operand of add is a source operand of subtract instruction. And this causes what is called as a flow dependency. So when there is a flow dependency, so what happens is, the subtract instruction has to wait till the result of the add instruction is obtained. So as an assembly language programmer, you may not know the underlying processor's performance features. So you will end up writing code which is in a way which seems logical to you. But when a compiler writer, what they do is they go dig into the manual and see, hey, so if I generating code rather than generating code in this fashion, I can generate a code in a different fashion. Like, for example, if there is a completely different instruction here, add R10 or R11 or 12. So the compiler will think, hey, I can as well insert this instruction between this add and subtract, and thereby make the program run faster. So these kinds of nuances, a compiler writer can keep in mind, because as against the assembly language programmer, so it will be torturous for me. And not only that, this is not, even let's say if the assembly language programmer does it, his code may not be performance portable, because in the next generation of the processor, this may not be the right thing to do, or there's a better way to do things, etc. But a compiler writer, he can work with the new generation of the processor, and he can include all this logic in his in the compiler that he is designing. So yeah, so when it comes to performance also, so if you rely on compiler, you will have certain advantages as against hand coding systems. That's number 2. Yeah. So usually this kind of thing works going directly right coding in Verilog or VHDL. It could be useful when you are working on extremely small kernels, which are very, very important. And you can hand design them. It's worth whatever the effort that you are putting to hand design them. Okay. But otherwise, you may want to use abstractions so that you will be able to build large and complex systems in a productive fashion, in a portable fashion, and they are easy to read, easy to debug, and all the good features are available. So, so this is the point I want to make. So using the right abstractions, be it for a processor or for an FPGA, it's important. So these are the 3 things that you have to keep in mind. As I said, one is productivity. Let's say if you want to deploy a deep learning a vision for a particular vision problem, let's say ResNet 50 or some Inception Net or some kind of deep neural network you want to deploy you want to design a hardware architecture for it. So if you go using Verilog way, I'm not saying we should not do it. So all I'm saying is when you are trying to build a complex system, so using high-level language abstractions improves your productivity substantially. And then second is, of course, performance is important. So this is where this is not a still solved problem, because when we use, at least in the context of compilers for sequential processors, it's a solved problem. Okay. But it's not a solved problem for multi-core processors. It's not a solved problem for GPUs. It's not a solved problem for FPGAs. So here we have to kind of struggle to get the performance while still using the high-level language abstractions. So I will put a question mark here because it's not, for sequential machines, single-threaded machines, it's a solved problem. But for the rest of the systems, it's not a solved problem. Okay, performance and portability. So yeah, we should be, if you design if you express your design on, for some FPGA, you should be able to, for a Xilinx based FPGA, if you design a system, you should be able to port it easily to an Intel based FPGA also. So that's an important thing. Okay. So this is again, you kind of get portability, but you may not get performance portability. So because you may have to structure your code to get the best out of an Intel FPGA, because earlier you may have optimized it for a Xilinx FPGA. All right. So same, this is in the context of FPGAs. In the case of processors, this portability is single sequential processors. This portability is not really a big problem. Okay, it's great. So now looking at so we want to see, so right now, if you look at the computing landscape, so there are three things. One is multi-core systems, multi-core. So when we talk about multi-core CPUs, it's primarily Intel and AMD come to mind, and even ARM is competing in this space. And then we have many core GPUs. So when we talk about these things, it's primarily again NVIDIA comes to mind, and then FPGAs. And actually, there are few other custom accelerators. We will talk about them later. So from single core processors, okay, from single core processors, we moved to this space of multi-core CPUs, many core GPUs, FPGAs, etc. Okay, how did we land up here? It's a kind of a bit of a historical look, but it is worth kind of reviewing these ideas once. So in this context, I want to bring to your attention, there is a HIPC 2021 challenge, HIPC 2021 challenge. In this HIPC 2021 challenge, they have 3 tracks, one track for multi-core CPUs, other track for GPUs, and other track for FPGAs. I circulated a message in this context already to the student groups. Hopefully, all of you got that message. So I encourage you to participate in registered. You can participate in more than one track. So you check on that context on the contest and see how you can participate. It would be a fun thing to do, because you will be there. I think you will get a problem and you have to optimize, write a program or build a system which optimizes the performance of that system. It's just not you write some algorithm to solve the problem. Usually in programming contests, it's all about, I guess, there is a tricky problem, you solve it, and in some bounded time. So this problem is slightly different. This challenge is slightly different. So you have to optimize for performance, and you will get enough time. It's not 2 hours, 3 hours. I think you will get a month's time to solve the problem. So you will, during that process, you'll end up exploring lots of interesting things these architectures have to offer to get the best out of them. Okay. So coming to, I'll quickly go through the history in the interest of time. So if you look at when 2000 till 2002, the way things used to work is processor manufacturers, they used to give better performance by coming up with better and better microarchitectures for the processors. All right, like for example, in your CSO course itself, you will see, you start the course with, you first learn instruction set architecture, and then you design a processor for that instruction set architecture. And that processor possibly executes only one instruction per clock cycle. There is no parallelism. And then later on, you design a pipeline processor for the same instruction set architecture. So when you have a pipeline processor, you process instructions in parallel. So because of that, the effective throughput increases, and you will be able to execute more instructions per clock cycle and per unit time. And beyond pipeline processors, we have what are called as superscalar processors, where, like for example, here you can see down below, so multiple instructions are fetched. It's just not one instruction is fetched. Like for example, if you see here, there is a superscalar processor which fetches 2 instructions per clock cycle, or actually this looks like it is fetching 4 instructions per clock cycle. And then all those, it will analyze those 4 instructions and it will try to execute the instructions in parallel. Okay, it looks for dependencies between instructions. If there are no dependencies, it will execute the instructions in parallel. So the superscalar processors, like very sophisticated, they do tons of stuff under the hood, and they execute instructions in parallel. They fetch more than one instruction from the memory per clock cycle. So they are very powerful. So the next thing is, but in order for us to be able to, in order to have this complex logic on the chip to execute instructions in parallel, we need more transistors on the chip. So here we have what is called as a Moore's law, which says that the number of transistors that can be placed inexpensively on an integrated circuit doubles every 2 to 3 years. This is not a law, so it's just more kind of just for every 3 years, we will be semiconductor researchers will come up with novel techniques so that they can pack more and more transistors per unit area. And semiconductor researchers did it. So they worked hard and they are able to pack more and more transistors per unit area. So, and in fact, this density they kind of made sure that they doubled for every 2 to 3 years. And because of that, we are able to do this, have more and more complex microarchitectures. Otherwise, we will not have enough transistors to put all that logic on the chip. The second thing is as the transistor size decreases, like the critical path lengths decrease, and we should be able to operate the transistors with lesser power. And as the critical path length decreases, as the gate delay length decreases, then we should be able to run the processors at higher frequency. So these two things are good. Better microarchitectures and higher frequency are good because the same processor you designed 2 years back, now if you can, with a new technology, with new transistor technology, if you can increase the clock frequency by 50% or double the clock frequency, then the same program, you should be able to run it at a higher speed. So, but then there are problems. So the first is what is called as a memory wall. So the memory wall is, the processor is able to run very fast, it is able to execute instructions very fast, but it is not able to fetch the instructions at the same, but the memory, the main memory is not able to supply the instructions at the rate at which the processor is consuming. So this is what is called as a memory wall. And in order to bridge the speed mismatch between the processor and the main memory, so we use cache hierarchies so that the frequently accessed data can be stored on the cache. But there are certain applications. Some applications can use cache well, some applications doesn't use cache well. Some applications, they may have to be re-architected so we can use the cache well. So all these challenges are there. And when we come to FPGAs, we'll also face this problem. That is, the FPGAs, although they don't process instructions, the circuits on the FPGA, they can run at a much higher speed. And in order for us to be able to supply data to the compute unit on the FPGA, it's not easy at the same speed. So a lot of hard work that we do while designing accelerators which are targeting FPGAs, we have to work on this, how we can hide the memory latencies while moving data. So in the context of FPGAs, we don't any streaming instructions, but there's a circuit on the FPGA, and then the data we want to keep pumping into the FPGA so that the circuit on the FPGA can process. But we have to be clever, otherwise the circuit on the FPGA could be super good, but we may not be able to, it could all the time be waiting for the data to arrive. So we will be studying techniques in this course on how to hide this memory latency. And then the second thing is ILP wall. If you take a program, your microarchitecture could be super powerful and it can execute 20 instructions in parallel, but your program may not have 20 instructions worth of parallelism. that there are dependencies in it. Okay, so beyond certain level, it's not possible for us to extract more parallelism from the program because we hit a natural limit. The program may have a certain level of instruction level parallelism. Beyond that, you will not be able to extract. This is called as ILP wall. And the third is what is called as a power wall, because as you keep on increasing frequency, the power dissipation increases cubically. So this picture here, you can see if the power just keeps on increasing, frequency keeps on increasing, then the power dissipation will be so high that you will not be able to manage the heat. So because of that, actually, you can see most of the processors these days, if you look at their power, they kind of hover around the 3 gigahertz. 3 to 3.6 gigahertz is the frequency with which almost all the processors run. And this turns out to be a big thing for FPGAs. You will see later, FPGA, when the power numbers for FPGA are extremely competitive or way better when compared with CPUs or multi-core CPUs or GPUs. Okay, so that is the big advantage. So here, so this is, so because of these problems, one is, the first one is the memory wall, memory bottleneck. Second is the available instruction level parallelism. It is limited. We cannot exploit anymore. And the power wall, you cannot keep on increasing the clock frequency. So because of these things, what processor manufacturers, they took a different path. So they started manufacturing multiple cores within the same processor. So earlier, when we have a single core processor, so there is only one thread of execution. There is only one core. This is one processor, there is one core, there is only one single thread of execution. And so when you write C programs, in your C program, you have only single thread of execution there. But when you go to a multi-core system, so with 4 cores, you have 4 threads of execution. You have 4 cores. So you have 4 threads of execution. So if you just take a C program and try to run it on a 4-core processor, you don't get performance out of it because it will just use only one thread. So you have to parallelize your C program. Either you rely on the compiler to parallelize it, or you manually parallelize your C program. This is where I said, no, performance is not a solved problem when it comes to multi-core architectures or GPUs, because the compilers now, so there is a tremendous amount of research, but they are not powerful enough to automatically parallelize your C program. They are able to do codes which have some kind of properties, but it's just not a, but there is still lots of challenges in designing compilers which can exploit the underlying multi-core systems. Okay, so yeah, so we have all these multi-cores. This is like, for example, this could be the picture on your. This could be the architecture of the system of the processor that is there on your laptop now. So you can look at this, they will see there are 4 cores, and every core has a vector processing unit, which we call as a SIMD unit. And then there is a cache, which is core, which is bound, which is private to the core. And there is these are L1 and L2 caches, they are private to the core. And there is a last level cache, which is common for all these cores. This is, I just took an example picture, but depending upon the processor, like for example, L2 cache could also be shared. Maybe L1 cache is private. So, but this is an example thing. But the challenge here is when you write a C program, so your C program, it's not, you don't automatically use this SIMD unit. Okay, SIMD unit is something like this. So you can say something like A of, that means in your take the first 4 elements in the array, and of B, of the array B and array C, and add them, and whatever the result that is present, put it in A. And if you have things like this, your SIMD unit can execute, okay, can execute all the 4 additions in parallel. So if you have a for loop, but then what happens is when you write code, you don't write code like this, right? So what do? This is how you write the code. Plus I, A of I is equal to. So now the compiler has to figure out that this for loop that you have written, that it can kind of morph it into a form so that the instructions within the loop look like this as against this. Once the instructions in the loop look like that, then it can use the SIMD unit. It can use the instructions associated with the SIMD unit. So there are challenges. Okay, so there are challenges, and for the compiler, if you just straight away write a C program, it cannot. It will be able to. In some cases, it will be able to do. In some other cases, it may not be able to do. And then again, so if you, in order to get good performance, it is imperative that we use the cache memory well. If you don't use the cache memory well, then the program performance will be pretty bad. So how do we use the SIMD units? How do we use the L1 cache, L2 cache? How do we use LLC? Because using LLC is painful because there is a thread running here and there is a thread running here. This thread fetches some data, for its execution. And this thread, it fetches its own data. LO corresponds to this, let's say. And these red chunk and yellow, they fight with each other. So the red may evict the yellow data and the yellow data may evict the red data. So there is a cache interference that happens at LLC. So there are tons of challenges here in this context. Great. So programming multi-cores, like there's in terms of raw computing power that is available, you have 4 cores. Each core can compute, let's say, half gigaflop of 1 gigaflop or 1/4 teraflops of floating point computations. And if you have 4 cores or 8 cores, then the raw computing power available is a lot. But in order to map this raw computing power, in order to translate this raw computing power to application performance, it's not easy. You have to change your algorithm. Okay, the way you think about the algorithmic approach, you have to change. And you need to use appropriate language abstractions to express your parallel algorithm. You have to rely on compilers, you have to rely on runtime systems, and the operating system also plays a key role. When you go to distributed memory systems, the moment if threads keep switching, so like here, let's say there is a thread which is running here, and the data associated for this thread is loaded into L1 and L2 cache. Now a process context switch happens and this thread starts running on this core 1. Then what happens is all this cache data gets invalidated. So again, it has to reload all this data into this cache. So operating system also plays an important role in the performance. Okay, so yeah, and then the much more difficult issues like memory consistency models and synchronization primitives. Tons of things come into picture in order to get good performance for your program. So suddenly the complexity of the system explodes. Okay, so we were happy earlier writing our programs in C using GCC or some compiler and get good performance. But now you just move to multi-cores. There is a whole lot of things that you have to do to get good performance for your program. And then again, when you go to GPUs. So GPUs are not like a general purpose computing systems. The way the usual setup will be like this. On your computer, so I'm sure you would have a similar setup. You will have a CPU with cache and all, and then there is a PCI Express bus through which you're connected to GPU. And GPU, it's no, so it can do computations and it will have its own memory. Okay, the size of this memory may be 1 GB, 2 GB, or 4 GB, depending upon what GPU you are working with. So this GPU acts as what is called as an accelerator. Okay, this is not your mainstream computing thing. So your mainstream, your main thread will be running on this CPU. And if you want to offload a computation, then you have to transfer the data on which the computation has to act through a PCA bus. If you see here, the data you have to move from CPU memory to GPU memory. And then the GPU does the computations. That is step one is this. Step one, transfer data from CPU memory to GPU memory. And GPU does computations. This is step two. And after that, you transfer the processor results will be transferred back to CPU. This is step three. Okay, so again, there's a communication is a problem because communication latency is high, and we have to work hard in order to hide this communication latency. And the architecture of the GPUs is quite different from the architecture of CPUs or multi-core CPUs. If you see here, in the CPUs, we have each core, it is a very complex thing. But here, if you see in this particular GPU, this Kepler GK110 GPU, it has 15 streaming multiprocessors. Each one here, this is one streaming processor, this is another streaming processor, this is another, so on and so forth. And within a streaming processor, there are multiple small compute units are present. So the amount of control logic, all these compute units, they run in sync. Okay, so you can think of each of these streaming multiprocessor as a SIMD unit. Okay, one single SIMD unit. Roughly speaking, this is not a very accurate picture, but roughly this is what it is. So the way we program GPUs, it's pretty different, and because the underlying architecture of the GPUs is very different. And the compilers, it's not easy for compilers just to take a C program and then map it to a GPU so that all these underlying architecture is efficiently utilized. Okay, this architecture, it provides huge amount of raw computing power. You can see 1 teraflop of floating point arithmetics, 64-bit floating point arithmetic. This particular GPU can do. But in order to translate this 1 teraflop of application, computing power into application performance gains, you have to work hard. The compiler has to work hard. In fact, if you just take a problem, maybe when the initial versions of your program, they will be their performance will be pretty bad when compared to even a single-threaded computation. So you really have to work hard depending upon the problem, a couple of months, 2 months, 3 months, 4 months, in order to get good performance out of this GPU. Okay. Yeah, so let's keep going. So now the point here is, so we still didn't go to FPGAs. But whether multi-core CPUs or GPUs or FPGAs, programmability is a challenge. Okay, so there are different approaches to make for a programmability. One one approach is you build libraries. Okay, so like when there is a small set of people who know that architecture very well and they are experts, and they work hard and they build a library and you just use that library. Okay, like for example, maybe some deep learning library or for which make use of GPU, or some whatever you can see, or some image processing or video processing libraries which makes use of GPU. You just use those libraries in your applications and get your job done, and you don't worry about what is happening under the hood. Okay, it kind of works maybe for certain segment or for certain applications. there's a second approach. So this is the easiest approach, but less flexible, because many times, in real world, we cannot just use things in a plug and play fashion, because we want, there's always something in some fashion, our application is different and we want to do things differently. Well, but there could be some applications where you can just use libraries and work. And the second approach is the directives-based approach. So in directives-based approach, like for example, if you have a for loop here, you don't rewrite the whole for loop, but instead, like you can say some pragma, OMP, parallel, so some kind of directive hint you give to the compiler, and the compiler uses that hint to parallelize the code that is following that pragma. So OpenMP is useful for, it's a pragma-based approach for programming multiple processors. Similarly, OpenACC, it's a pragma-based approach for GPUs. And of course, this is the first approach. Second approach, and as we go this way, the complexity increases. Okay, so this is the most complex approach, where we use frameworks such as CUDA and OpenCL, and we understand the architecture of the system, and we write our programs so that we exploit the architecture. So this is the most difficult approach. In terms of productivity, it is less, but you will have greater control on what you would like to achieve. Yeah, so I think this is what we talked about now. So now we have seen multi-cores, there is a little bit of GPUs, and finally ASICs and FPGAs. So what is an ASIC? An ASIC is an application-specific integrated circuit. Your processor is a kind of an ASIC. It's a general purpose ASIC, but you can have ASICs now which kind of do some specific tasks. Like for example, you can have a special chip on your router so that it can process incoming packets at a very high speed. For the latest, the better example here is we have Google TPUs, tensor processing units. These TPUs are designed to handle deep learning workloads. And then similarly, Intel has something called as a neural stick. So again, this is an ASIC. So what happens is you can expedite computations using this special purpose ASICs. Okay, they can handle machine learning workloads. Earlier, ASICs were used. On your mobile phone, there can be a special image processing. There can be a special DSP processor to handle image, video processing, or any kind of signal processing tasks you may want to use. You may want to handle using the DSPs on your mobile phone, for example. So the challenge with ASICs is, so they give the advantage is they give very good performance because they are designed keeping some application in mind, and the power consumption is also very low. So in general, they are very good on the performance per watt metric. But the problem is designing an ASIC is very time consuming. It's very expensive. It could take probably 2 to 3 years in order to ship an ASIC out. Okay, so these are the challenges in designing ASICs. So you need to have, so you may want to go for an ASIC if the economies of scale are there. Like if you are just interested in 100 chips, you may not be, the market is very small, then going for an ASIC may not be a great idea. But if the market is large, especially if you take Samsung or any of these mobile phone manufacturers where the market is really big, they may want to invest in ASICs so that So whatever the thing that they kind of invest in, it pays them off because there are so many people, millions of units, mobile phones they can sell using the ASIC that they develop. So if you take, I'll take kind of 5 minutes and conclude this session. So if you take ASIC flow, this down the lane, maybe in the next class, Dr. Padmini can talk little bit, may talk a little bit more about this, but you don't need to get into too many details. So here we start with a functional specification. That is what we are supposed to do. And then we come up with a HDL, hardware description language. Using a HDL, we express the architecture. So this is step one. And then we do behavioral simulation to check if it is working all right. Okay, and then we do synthesis, we do timing analysis, and then after after we do timing analysis, again we have to go to the next steps like floor planning. How do you lay out the circuit on the ASIC? So this is you can see, as you can see, there are multiple steps are involved, and every step here, it's a very complex step. Okay, so after everything is done, you kind of hand it off to foundry where they give a chip for you. You have to bring that chip back, and then again you have to test it to see if it is all doing good. And if there is some problem there, then it's going to be very costly because you have to go back and redesign, find out what is the problem, and redesign and again go to foundry. So ASIC flow is very expensive, time consuming, money, time, and you may lose competitive advantage on your, if you make a mistake, then it could cost you quite a bit. But on the contrary, if you go use, if you have programmable hardware, I have an extremely simple picture of a programmable hardware here. So here you can see for the time being, if you just focus on this particular this particular part of the picture, don't worry about this. So you see this three input, you have a tree of multiplexers, and using this tree of multiplexers, it is possible for us to realize any 3-bit Boolean function. Any 3-bit Boolean function, A, B, C. So this is F. So you can write the truth table here: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on and so forth. You can write the truth table here. And the Boolean function can be anything. It can be an AND gate, OR gate, or whatever it may be. So depending upon which Boolean function you would like to realize, you just fill in these registers. So when you fill in these registers, then and if it is 0, 0, 0, then the value that is present here, it flows at the output. So using this array of multiplexers, tree of multiplexers rather, it is possible for us to kind of come up with a programmable hardware. Of course, I'm giving a very simplistic picture, but this is the intuition behind how FPGAs work. And if you look at a generic FPGA architecture, so you have so many such LUTs, logic blocks, VRAMs, and routing networks between these logic blocks. So when you take a complex design, so we kind of put that complex design, program the FPGA in such a way so that the LUTs are appropriately set, the routing networks are appropriately set. So everything is kind of properly set. So the net architecture or the net hardware that is present on the FPGA is equivalent to what you have in mind or what you have specified. So here I gave you two examples of FPGAs. On the top side, you have Altera. Altera is now acquired by Intel. So it is they are Intel FPGAs. On the bottom, you have Xilinx. Xilinx is still not acquired by anyone. And so you have, so you have Kintex FPGA. And if you look at the FPGA flow, so you can see, you do a behavioral simulation, you do synthesis, and you do some level of timing analysis. And then after that, you can put it on an FPGA and run. And if it's not working, you can go back and do it. And the cycle is fairly, it's not in the order of months or years. You can do it in the order of days or weeks, this cycle, if something doesn't go well for you. So whether we want to use ASICs or FPGAs, so ASICs give very good performance. But if you want to try out something new, you cannot simply go ahead with an ASIC. You just want to first build it, try it at least on an FPGA and see how it is working. And the power definitely ASICs, the power efficiency of ASICs is way better than FPGAs. But in terms of development cost, FPGAs, the development cost is very low when compared with ASICs. And so this is low cost in high volumes and large time to market. All these things we spoke. So ASICs, high performance, low power, low cost when there is economies of scale, and there is a large time to market. But whereas when we go to FPGAs, they are readily available, low development costs, they are reprogrammable, short time to market, but the performance is not as comparable to ASICs, but they are comparable or better than GPUs or multi-core systems. Yeah. So power also, when compared to multi-cores and GPUs, the power savings will be substantial. So the homework for the next class is there is a very, very interesting paper that is, you can see here, 3 ages of FPGAs, a retrospective on the first 30 years of FPGA technology. I strongly recommend you to read this paper before you come to next class, so that it will give you, it's a very good paper. It gives a very good overview. So now, I would like to conclude today's lecture on this. So the most 3 important parameters of importance when we consider a system is programmability, performance, and in fact, when we talk about performance, maybe performance per watt, this is 2, and number 3, portability. So when we look at FPGAs, in terms of they are not easily programmable. There are lots of challenges in programming FPGAs, especially when we use Verilog, VHDL, low-level hardware specification languages. There are lots of challenges. And so that's the reason. So there's lots of tremendous amount of effort or research happened in the last 3-4 years on lifting the abstractions. Okay, so primarily HLSC, it's a very important thing. And in this course, we use what is called as an OpenCL framework for hardware specification. And under the hood, OpenCL uses HLS. So it is like this, like you have HLS and HLS. The specification that you make in HLS, it gets mapped to Verilog or VHDL by the compiler. This is HLSC, this is C++. And then OpenCL is one level above. And then above, there are some research projects on how to specify some architectures using domain-specific languages. So that from you specify whatever you want in a domain-specific language, and the compiler will map it to either OpenCL or to HLSC. Like an example of this is we have Halide. Halide is a domain-specific language for image and video image processing. And similarly, from within IIIT, we have Flowpix, although it's not yet open source yet. So where you specify, you completely forget about the architecture or anything about FPGA, you just focus on your application and express it using these domain-specific languages, and there are compilers which can map them to OpenCL or HLSC or C++ or Verilog. Okay. So yeah, the game here is all about providing the right level of abstraction, while and the compiler should be able to map these abstractions to a lower level while giving the appropriate performance per watt. And portability, for when the design that you make for one FPGA, should be able to apply, take it over to other FPGA, but this is questionable. I'm not sure about this. But at least if these two things are satisfied, it would be great programmability and performance. But this is also a very interesting question. So let's see, we will try to investigate this question as a part of this course. I would like to kind of at this point highlight you to two things. Chisel is a very big project supported by Berkeley, and I guess so, and BlueSpec system Verilog, earlier it is supported by MIT. So these are also two very nice hardware specification languages. We will not be focusing on them in this course. Our focus will be primarily on OpenCL based specification language targeting Xilinx FPGAs. That is our goal. So with this, I will conclude today's lecture. What I would like you to say is, we will bring your 40% or substantial portion of this course is on the project. You should work on build an interesting project from the domain in which you are interested in, be it computer vision, speech processing, or or natural language processing, or robotics, or I don't know. So what bioinformatics or blockchain technology, whatever you have. So we would like to identify problems, interesting problems from the domain, and try to solve those problems using the tools and techniques that you learn from this course. So we will equip you, we will teach you, we will learn together all the architectural approaches, how to use the tools, the flows, everything in the first 6 weeks. We will try to get the foundations solid. And after that, we will kind of study different problems and see how we can accelerate those problems using the tools and techniques that you have learned. So that's all I have for you today. And if you have any questions, please ask. You can ask me now. One important thing I would like to mention is after the add drop date is over, we will start the process for giving you accounts on the AWS Educate Classroom, so that it is possible for you to use the cloud to run these design tools and to run it on FPGAs. Okay, that we will do after the add drop date is over. And those of you who are seriously auditing, so please do send me a mail. I'll try to see if I can add you to the AWS cloud. Depending, I may or may not be able to do it depending on the availability of resources, because we have a maximum of 50 student limit on the AWS cloud. The credit limit is there. Okay, so okay, that's all I have. Oh, add drop date is already over.
Sir, is the project team-based or solo?
Project, we will have 2 students per project. That's the plan. Just want to quickly check the add drop date is over. I thought it is. So we have a final list of students then.
Sir, I think the withdrawal.
Actually, there is another add drop this weekend.
There is an option still to withdraw, I think.